Algebra 2. This is 723, which is multiplying radical expressions. So by the end of this, you should be able to multiply radical expressions that have the same radicand and index. So what we mean is, if we have something like the square root of 3x times root 5y, because these are both square roots, and because they both have 2 on the outside, and we'll say in parentheses, even though you can't see it, you can multiply them. Right? So when we have square roots like this, you can assume that their root is 2, even though you can't see it, right? So you can assume that you have a little 2 right there. And so because those are both square roots, what we can do is we can rewrite everything under one giant square root, and we can say this is the same thing as 3x times 5y, and they can all be multiplied. So this works for multiplication. You can take separate square roots like this and combine them under one, and then say that this is the same thing as the square root of 15xy. Okay? And so this rule where we can multiply things that have the same root, we call this the product property of radicals. Okay, and let's say you had something like a cube root. So you could have the cube root of 4x. Well, actually, I don't want to do that just yet. Let's say we have the cube root of 7x times the cube root of 2y. Okay, so these are both cube roots. They're being multiplied. So we can put this all under one cube root. So I have 7x times 2y, and we could simplify that to be the cube root of 14xy. Okay, so this is a case where we can see our root, and you can see how it stays the same the whole way through. So that's the one thing to remember about this when you're multiplying radicals, is your root never changes. Okay, so this is 3 the whole way through. So that's a pretty simple, that's one of the simpler things that we're going to be doing today, and then we'll be throwing some twists on that. The other thing that we need to talk about are complex conjugates. And so complex conjugates are things in parentheses that include radicals, or later on in the chapter they'll include imaginary numbers, but they're things in parentheses that are being added or subtracted to each other. And so the example that you're given on your handout is root x minus 3 times root x plus 3. So these are complex conjugates because they are the exact same thing inside those parentheses. One is a root, or both have a root x and both have a 3. And the only thing that's different between them is the sign. So one has a negative and one has a positive. Okay? Now, you can, there's a shortcut and a long way to multiply these. Let's see, and so we'll do that on another piece of paper. So if we take a look at this again, we have root x minus 3 times root x plus 3. Okay? And so the long way to multiply these out, in the way that you already know how to do, is to FOIL. So we could just FOIL those out. If we take our firsts, root x times root x, well, let's see, I'll write this all out so you can see what I'm doing, and then I'll simplify it as we go along. So we have root x times root x, my outers, so that'll be plus 3 root x. My inners, that'll be minus 3 root x. And then my last, negative 3 times a positive 3, that's a negative 9. So we can simplify a few things here. So a root x times a root x is just x. And then 3 root x minus 3 root x, the 3 root x, well, that disappears. And so we're left with x minus 9. And so that's your answer there for multiplying that out. Now, there's a shorter and faster way to do this. You can go ahead and FOIL, because then in that case, it's just the same thing that you do for everything. But if you want to learn the shortcut, which is the exception to all of this, let's see. So, the shortcut is going to be the first squared minus the last squared, okay? So my first term here is root x, so I would take root x and I would square it, and then my shortcut says throw a minus in, and then it says take your last and square that. So my last is 3, and then we square that. So root x squared is just x, and then a minus, and then 3 squared is 9. And that's it, and we're all done, okay? So you can use that shortcut if you like, or you can just FOIL. Alright, so with that, we're just going to jump into the classwork. And we'll do as many of these examples as we can, because there are lots of different types of multiplication of radicals that we could come across. So for number 1, we have root 2 times root 8, right? So both are square roots, so we could rewrite this all as the square root of 2 times 8, which is the square root of 16, which is just 4. And we're all done. For number 2, we have root 6 times root 8, which turns into the square root of 6 times 8, which is going to be the square root of 48. So 48 is not a perfect square, but we've come across this a lot. And the largest perfect square inside of 48 is 16, I'm sorry. So 48 is the same thing as 16 times 3. And we know the square root of 16 is 4, and we can pull that out. And the 3, we can't do anything with that, so we leave that on the inside. And so our answer is 4 root 3. For number 3, we have root 7 times root 28, so we can combine this under one radical and have the square root of 7 times 28, right? And 7 times 28, well, I don't know that off the top of my head, but that's okay. It might be better that I don't know that off the top of my head. I know that 28 is the same thing as 7 times 4. So let's break this down a little bit. So I probably could get away with doing this without a calculator at all. So I'm going to keep the first 7 that I have in there. And then that 28, let's rewrite that as 7 times 4. Okay, well now, let's see. I have 2 7s, and I know that that's a perfect square. That's the same thing as 49, right? And then I have 4. So now I can take the square root of 49, which is just 7, and I can pull that on the outside. And I can take the square root of 4, which is 2, and I can pull that on the outside. And I've pulled everything out of the radical now, so I don't have anything left on the inside, so I can just multiply that out, and I get 14. And that's my answer, and I'm all set. So that's a good example where it might not be to your benefit to multiply everything out and get some really big number. It might be a good idea to keep things small and to kind of break things down and group them by their factors. And then see what perfect squares you have. So we can try that strategy with a few other ones that we do today, okay? So let's take a look at number 4, which is some cube roots. So for number 4, we're going to have cube root of 8 times the cube root of 32. So we can, both of those are cube roots, so we can put everything under one cube root. So I have 8 times 32. Okay, so I don't know what the cube root of 8 times 32 is off the top of my head. I know that 8 is a perfect cube. So, well, how do I know that? You can remember that 2 cubed is 8. Okay, so that's how I know 8 is a perfect cube. So I could break this down. Well, I have my first 8, and I'll leave it like that because that's a perfect cube. 32, I know, is the same thing as 8 times 4, right? And we've got another 8, which is another perfect cube that we can handle easily, and then 4. So the cube root of my first 8 is 2, so I can pull that out. The cube root of my next 8 is also 2, so I can pull that out. And then the cube root of 4, well, 4 doesn't have any perfect cubes in it, so we can't do anything with that. So that's as far as we can go. So we'll leave that on the inside. So then we can multiply the 2 times 2 on the outside, and we get 4. So I have 4 times the cube root of 4. And we're all set. For number 5, I have the square root of x cubed y to the 5th times the square root of xy cubed. Alright, so if we put everything under one radical, I have x cubed y to the 5th x y cubed. So x cubed times x is x to the 4th, right? So right now I'm just simplifying things. Y to the 5th times y cubed is y to the 8th. Now to take the square root of this, I can just divide all of my exponents by 2. And that'll give me x squared y to the 4th, and I'm all set. Moving on to number 6, we have the same situation, but with cube roots. So I'm going to have the cube root of 9 x to the 4th y squared times the cube root of 6 x squared y to the 7th. Okay, so multiplying these out, we'll have a cube root. So I'm just going to put everything underneath one radical so we can see what it looks like. Okay, so we can multiply things out. So the 9 times 6, well, I know that's 54. X to the 4th times x squared, I know that's x to the 6th. And then y squared times y to the 7th, I know that's y to the 9th. Okay, so now cube roots, well, 54, I'm trying to think of perfect cubes inside of 54, and we have 27. So 54 is the same thing as 27 times 2, and then I have x to the 6th, y to the 9th. So the cube root of 27 is 3. I can pull that on the outside. I can't do anything with the cube root of 2, so I'll have to leave that on the inside. To do the cube root of x to the 6, we'll just take that 6 and divide it by 3, so that'll give me x squared. And then to do the cube root of y to the 9th, we'll take that 9 and divide it by 3, and we'll get y cubed. And so that's it. We're taking care of everything, and we're all done. Let's go on to number 10. So for number 10, I have root x times root x plus root 3. So in this problem, we're taking the root x on the outside and distributing it across what we have on the inside. So I'm just going to write everything out so you can see, and then I'll go ahead and simplify it. A lot of this stuff you might already be able to do in your head, but for now, I'll just write everything out. So we'll have root x times root x plus root x times root 3. So whenever you multiply two square roots of the same thing, the square root just cancels, and you're left with just one of those. So that means I'm going to have just x. And then these two square roots, the root x and the root 3, we can combine under one and say this is the square root of 3x. So there's our answer, x plus root 3x. let's take a look at 11. We can do something similar here. So I'll have root x times root x minus root 2, right? And so I'm going to take the root x on the outside and distribute that across. So I get root x times root x minus root x times root 2. So root x times root x is x, and then root x times 2, so that'll just be minus root 2x. Okay, and that's it, and you're all set. So let's take a look at number 12. So for number 12, we have root 4x on the outside times the square root of 32x minus root 18. Alright, so we're going to take this root 4x and distribute that across. So, let's see. Well, square root of 4, excuse me, 4 times 32, I don't know what that is. So what I could do, I'm going to have to break it down anyways, because I could write this as 4 times 32, and then break them down separately. And then x times x is going to be x squared. Okay? And then the same thing, 4 times 18, I can't think of that off the top of my head, so I'll write this as 4 times 18, and then we have x. Alright, now, so we've got a 4, 32, the largest perfect square inside of 32 is 16, so we can break that down into 16 times 2, and then we have x squared. So then, for the next one, we have that 4, the 18, we can break that down into 9 times 2, and then we have x, okay? So, the square root of 4 is 2, we can pull that out. The square root of 16 is 4, we can pull that out. This 2 we'll have to keep on the inside, and then the square root of x squared is x, we'll pull that out. So the square root of this 4 is 2, we'll pull that out. The square root of 9 is 3, we can pull that out. And then this 2, well, we can't take the square root of that, so that stays on the inside, and that x, we can't do anything with that, so that stays on the inside as well. So we can go ahead and simplify some of this. So 2 times 4, we'll get 8x, and then we have root 2 minus 2 times 3 is 6, and then we have root 2x. Okay, now our x's are in different places here. One's outside the radical and one's inside the radical, so we can't do anything to combine them. So for this particular problem, this is as far as we can go, and that's our answer. Let's go on to number 20. So for number 20, we have root 2 minus 1 times root 2 plus 2. And this is something that we're going to have to FOIL. So if I do my first, root 2 times root 2, it looks like that. My outers, that's going to be plus 2 root 2. My inners, that'll be minus 1 root 2. And then my lasts are minus 2. So root 2 times root 2 is a positive 2. And then positive 2 root 2 minus 1 root 2, that's just going to give me a plus 1 root 2, and then we have that minus 2. So we can simplify 2 minus 2 is 0, so those cancel out. So the only thing we have left is just a root 2, and that's our answer. So going on to 21, we'll have the same kind of process there. So we'll have root 3 minus 3 times root 3 plus 1, right? And we can FOIL. So root 3 times root 3, multiplying my first, and then my outers, plus 1 root 3, so that'll be plus root 3, and then my inners, minus 3 root 3, and then my last, minus 3. So root 3 times root 3 is 3, and then 1 root 3 minus 3 root 3, so 1 minus 3 is going to be a negative 2 root 3, and then minus 3. So again, 3 minus 3, that cancels, and your answer is just negative 2 root 3. Alright, so we have two more. So 22, those are complex conjugates. So we have root x minus 3 times root x plus 3, right? And so we said you could, these are complex conjugates because we have the exact same thing in both sets of parentheses, and the only thing that's different is the sign between them. This is a minus, this is a plus. And we could go ahead and FOIL and do this out the long way, or we could use our shortcut, which is just our first squared minus our last squared. So let's do that. So that means we'll have root x, the whole thing squared, minus 3 squared. So root x squared is just x, and then 3 squared is 9. And that's it. And so then we can do the same thing for number 23, which is going to be root x minus 4 times root x plus 4. So we'll do our first squared. So again, we'll have root x squared minus our last squared, right? So minus 4 squared. So we know root x squared is x, and then 4 squared is 16. And so your answer is just x minus 16. So that's the end of 723, and so hopefully you know enough to try the homework.